My name is Maksym. I work for the NEAR protocol. We are a blockchain. This talk is about smart contracts written in Rust. So I know that not many people know what smart contract is, but there are many more people who know what AWS Lambda is. So let's start with that. So AWS Lambda is this alternative. What? Not loud enough? Okay. AWS Lambda is this alternative computing platform that Amazon has introduced as a different way of running your microservices. Usually when you write a microservice on a cloud platform, what you do is spin up a virtual machine. You have this service there spinning, waiting for some events like requests or some internal timers, cron jobs, and then it replies to the requests. And what happens is that in between those events, it is idle. It doesn't do anything but costs money. Amazon Lambda, when it doesn't reply to the event, it doesn't do anything. It doesn't cost money, which is great. And then when it gets an event, like a request, it wakes up, replies to it, and then goes back to sleep. And that's what it means to be event-driven. So AWS Lambda is event-driven serverless computing platform. And you can think of it as you basically deploy some function to the cloud saying, this is how you reply to this type of the requests or this type of the events. And then your function is being also automatically provisioned. So you don't need to think how many machines you need to run, what kind of machines, how to load balance this whole thing. You just deploy it to the cloud and it's all handled for you. So smart contracts are very similar to Lambda, but they also have one additional nice property is that they're decentralized because, well, smart contracts are usually on the blockchains. And most of the blockchains, some of the blockchains are decentralized. Our blockchain is decentralized, which means there is no single entity like Google or Amazon or Microsoft who runs your stuff. And this is, people like it for many reasons. Some people just, it's a question of trust. They just don't trust this single entity. But there are also practical reasons why this is better, even if you don't care about trust, why this is better than running on the cloud. And I'm going to show you later why. So the way you run the smart contract, and this is like a short intro to the blockchains, is you have this blockchain, which is nothing else but just an immutable history of those events that we were talking about, but like batched into blocks, and the blocks are linked into the blockchain. And it is constructed by a group of, let's say people running a validator node. And collectively, they build this blockchain. They decide what is the sequence of events, how to batch it into blocks, etc. And ideally, if it's a real decentralized blockchain, it should be very robust against adversaries and computers just going offline and stuff breaking. For many blockchains, there's as long as you have less than 33% of adversarial participants and service being offline, it should work completely fine. And the reason why we like it is there are many histories out there, many stories, like very recent one with the Google Cloud, when it just goes offline, and in huge amounts. There was basically a story where an engineer in Google entered a wrong command in a terminal and shut down a whole bunch of servers across the globe. And that was so huge it affected small to medium businesses everywhere. It was also took a long time to fix this. And realistically, small to medium businesses, they don't diversify the cloud infrastructure. They usually just pick one and run on it. So when shit goes down, they're screwed. Their business is not working. Even more so, they're not running more than one machine, realistically. And actually, in most cases, they have only one or two engineers, or maybe even half engineer, maintaining this whole thing. So when it goes down for quite a long time, and businesses lose money. And the same thing happens to Amazon and Microsoft. This is a routine. It happens all the time. So if you were running the smart contract on the blockchain instead of the AWS Lambda, if someone types the wrong command in the node, it's just their node that goes down. And as long as you have 30%, less than 33% of those things happening in your network at the given moment of time, your network is completely fine. and you won't even notice the difference. And the other reason is usually the code that runs smart contracts is open sourced. Well, at least in our case, it's open sourced, which is really great because vulnerabilities in the open source code are noticed much faster and fixed faster than in the closed source code. And for most of the cloud infrastructure out there, they're running closed source code. And the most egregious example of bad stuff happening because of that is Cloud Bleed. So Cloudflare is this cloud services provider that once they basically misconfigured their reverse proxy and they were spreading the private user data all around the internet in huge volumes. And that went unnoticed for 5 months. So, and the volume was so huge that Google search engine started indexing it. Like it was, comparable to some web pages volume. And the way it got noticed, that Google engineer in Zurich was debugging the Google search. He was like, oh, what's this data here? Looks very private to me. And he tweeted to the Cloudflare saying, hey, something's wrong happening. But that went unnoticed for 5 months. And that was because this stuff was like closed source. No one was looking at it, but with the blockchain, usually the code is scrutinized. So more people looking at it, better. I mean, we all know the story that vulnerabilities in like Linux are noticed much faster than vulnerabilities in closed source operational system like Windows. So this is just a brief overview of what is inside the node that runs your smart contract. And this is pretty much the same high-level architecture for all blockchains out there. So there is a split between a blockchain layer and the runtime layer, and the blockchain layer does all this magic with like peer-to-peer networking, relaying information between the peers, organizing them together, like some spam protection, like balancing. There is consensus that allows the peers to agree together on what to run. There is storage. There is RPC API that allows the node to look like a microservice. Well, the other part is the runtime layer, and this is what we're going to be focusing on today. It has these 3 major components: virtual machine that runs your smart contract code, the code itself, and state storage. State storage is basically where you store the state that the code changes. So like the side effects of running the code are preserved in the state storage. So there are basically 2 camps in the blockchain world about what this virtual machine and the code language should be. And one of them is, let's use generic virtual machine like WASM. So this is pretty much always a WASM virtual machine. And some generic language like Rust and TypeScript. Another camp is, let's use specialized virtual machine plus some specialized language. And usually they write their own virtual machine language. And the pros and cons are quite straightforward here. With a general purpose language like Rust, well, there is existing tooling. There are libraries you can link in your code. You can simply just find your answer on the Stack Overflow. This is a huge advantage. We all know that. The community is there. They can answer your questions. Some people, you can even find someone to hire to work on your code. And also because these languages, like Rust and TypeScript, existed for long enough, that means the kind of passive validation by the community. Meaning, like, if they are popular, they're good. And the features are polished. And so it's easier to use them. And they're also Turing complete. With specialized virtual machine and specialized language, the pros is that it's fitted to the blockchain. Very frequently, it's fitted to a very specific blockchain, so it's supposed to be better in terms of whatever properties we'll see later. And in some cases, people dream of formal verification for the smart contract, so they try to make a language that's formally verifiable, and quite frequently, it leads to a functional language which is not Turing complete. The cons is that it's a niche language, right? The chances of finding someone knowing this language is quite low. So unless you're Ethereum with Solidity language, but Solidity is also really hard to work with. There are not enough tooling for this. The people speaking against WASM usually bring the point that WASM was not designed for the blockchain initially. And what they are looking for in the virtual machine is the following set of properties. They want this to be platform-independent virtual machine or portable. which is actually what WASM was designed to be from the very beginning, but for a different reason. Like people wanted it to be runnable on all kind of browsers, operational systems, hardware. So it is actually portable. Then determinism is trickier. It was not designed to be deterministic. With the blockchain virtual machines, you'd want for the same input to always get the same output of the code. And even more so, you want it to be always the same sequence of operation that your machine performs independently on when you execute it on what hardware, which is actually harder, the same sequence of operation. And it's really easy to achieve this with Rust. Just ignore floats. And maybe in the future, they're also going to have deterministic floats. Then sandboxed execution compilation is a problem. Since this is blockchain, it's supposed to be super safe. People always try to hack blockchains. You don't want your code to fiddle with the actual node, and which is like one type of sandbox. Another type of sandbox, and you want to avoid compiler bombs, which is basically when you compile your smart contract already written in Rust into the low-level machine language, you want it to be actually linear or close to linear time that it needs to be compiled, because otherwise people can write something that just hangs your node and you're done. So with certain executors, I think WASME written by parity actually says the safe from the compiler bombs. You can achieve that too. Then small size of the compile code. This is also something that WASM supports by design, because WASM is like people are supposed to be actually loading it through the internet, so it's supposed to be like really small size once it's in a WASM format, which is the same requirement for the blockchain. And it's sort of close to the machine code in terms of the performance. Like there is not a huge overhead of running WASM versus running the same program written in machine code. Then if we are using WASM with Rust, there are also some bonus points. I mean, if we're writing Rust contracts and compile them in WASM. So the first one is tooling and community. We discussed that. Code transfer, really good. And memory safety, also pretty neat. The previous talk discussed why memory safety is important. But also zero cost abstractions, and this is something that Rust is very proud of. So there are many libraries that are so-called zero cost abstractions in Rust. And just to remind you, zero cost abstraction is what you don't use, you don't pay for, and what you do use, you couldn't hand code any better, which means if some library boasts to be a zero cost abstraction and you link against it and you use some of its stuff, the compiled code in terms of the size and performance is pretty much, you cannot write the same thing manually better. Or it's almost like within the same margin there, which is really important for the smart contracts because we care about performance and the size. We discussed that. So these days there are multiple blockchains and projects that that do Rust APIs. One of them, the first one, is our blockchain, Near. Then there is one called Wavelet from the Perlin. There is eWASM, which is like a large scope, like project with a large scope. Basically, they work on standardization of how to run WASM on Ethereum-like blockchains, like not necessarily Ethereum, but like Ethereum-like blockchains. Then there is Ink from Parity and Mantle from Oasis blockchain. There is the one deprecated. It's called PWASM with Fleetwood, and it used to be used for the Kovan, which is a proof-of-stake blockchain by Parity. So all of them, they have this architecture in common, which is how they interface with the blockchain, how blockchain interfaces with them. So you have this WASM executor running Rust contract, and you have two types of the interfaces: contract interface and blockchain interface. Contract interface is how blockchain can access the contract, like what the methods on the contract are available for the blockchain. And the blockchain interfaces are what the methods of the blockchain are available to the contract. And here I split it in two. There is part of this interface for the blockchain layer, like what is the current block index, what is the balance of the user, and the second one is the state storage, which is methods that you use to access the state that you save on the blockchain. So let's walk through some of those APIs, Rust APIs. and start with eDSL-based APIs. So eDSL stands for Embedded Domain Specific Language, which means that you write your contract in Rust, but you have to follow certain patterns, certain rules in order for it to actually become a smart contract. And this is an example of inc from parity. This is a very simple smart contract here. It's an called incrementer. What it does, it just stores one value, and then it exposes only one function called increment, and you call it, and it increments this value by a given amount. It also does like logging through this println method, which saves this information on the blockchain. So what is the contract interface and the blockchain interface in here? So contract interface is this deploy function that you have to declare with it. And you see it's basically initializes the contract. Like once you deploy it on the blockchain, that's what is being called. Then you have to also wrap it into this macro called contract with bang. And what it would do, it would generate other contract interface stuff that you actually don't see. Then the blockchain interface is like println. This is the blockchain interface. That's like what you can call on the blockchain, like log this string. And the part of the blockchain interface responsible for the state is basically exposed through the storage wrapper. So all the stuff that you want to preserve on a blockchain, you need to use the storage.value and wrap your stuff with it. And unfortunately, it's only for the primitive types and some hash set kind of thing. So this is another Rust API. It's for the same type of the contract. You see some stuff is different here. You need to decorate your struct with derived service. You have to add the function called main in here. You have to add another function called new. You have the first argument as context. That's how you access the blockchain interface. The other type of the API, specifically ours, is the non-invasive. We call it non-invasive API. And the idea behind it is we want for the developer who writes Rust to just take whatever Rust they have and like put like one line in it, and it becomes smart contract without like modifying the refactoring the whole thing. So the same smart contract that you saw before with non-invasive Rust API would look like this. The only thing here that is from the smart contract is this decorator near binding on the impl section. And what it does, it basically makes this thing a smart contract. And so we derive the contract interface for you. And we derive the part of the blockchain interface responsible for the state for you. And how do we do it? It's magic. Meaning it's automatically generated injected code using macros. And it doesn't quite bounce off the tongue, but abbreviations are hard. So what does it do? Because it's a procedural macros, it is able to modify the AST of the code that it decorates. And it traverses it, and it figures out that those public methods, those should be contract APIs. And like whether it's mutable self or not mutable self actually tells you whether you need to save the state of the contract. So when it does it, when it iterates over this code, it decides what kind of code it needs to generate and inject in here. What else it does, it uses this default trait that you can derive in some cases or implement yourself to initialize the contract. And what else is happening is that the contracts on our blockchain, at least, they can be written on different languages, not just Rust. So we want them to communicate with each other, but then we cannot use like Rust types just like straight away. We also add JSON serialization, deserialization in there, injected in there. And we also allow you to take any struct, and it's going to be preserved on a state. You don't need to wrap it like with storage value or anything like that. We're going to use also another kind of serialization, because serialization in Rust is a zero-cost abstraction, and it adds no significant overhead. And this is the expanded version of it. So you see, we generated this mess in here, and it has all kind of serialization stuff happening, all of the methods that we haven't seen exposed. And the cool thing about using this kind of format for the contracts is that you can actually generate eDSL style API using this. So like, we could have defined mental binding, and then just because procedural macros are so powerful in Rust, you can just like iterate over this code and generate everything that you should have written manually for the eDSL language. And there is also another blockchain from Perlin. It's called Wavelet, and they kind of arrived to the same idea independently from us, which means that this is the good idea. They just decorate it, they have a different name. We have nearby engine, they have smart contract in there, and pretty much the same thing, except they don't have parsing of the JSON, so you need to pass this parameter struct explicitly. It's like one big difference. So how do we unify this whole thing? Ideally, we want people to not think what blockchain they are developing for. Like if you're a Rust developer, we want you to just like write some smart contract and be able to deploy it anywhere. And this is one of the purposes of WASI, WebAssembly Systems Interface, to be like very universal. And the idea behind it is that you have this interface that your WASI will use to communicate with whatever runs it. And it's modular. So one of the modules can be smart contracts, which is actually what was envisioned initially by WASI. And in this smart contracts, you can expose the module, you can expose whatever you want to be accessible to the smart contracts from the blockchain. And so if we standardize this, then the Rust smart contracts can be run universally on all blockchains that support WASM. So we talked that there is contract interface and blockchain interface. So blockchain interface would be handled by WASI, and the contract interface is something you can generate with this procedural macro, like you saw before. And once this WASI standard goes through, you basically, when you move from one blockchain to another, you just switch this decorator there. Unfortunately, there also might be some blockchain-specific APIs that you're going to be calling, but I mean, this is on you if you want to have something like super specific calling in your smart contract. So there are also some nice-to-have features that we want to see in smart contracts. One of them is that we want to have asynchronous cross-contract calls, like you want to call one smart contract from another smart contract on the blockchain. We want to unit test and integration test them. We want it to be type safe, and ideally we want to have model checking. So asynchronous calls would look like this. You have some smart contract A creating a promise, which is very similar to a feature in Rust that would call smart contract B, and then another promise that calls smart contract C. And why we want it to be asynchronous, because when we can do it simultaneously, we can issue two promises and like let them run in parallel. And then we can, ideally we won't want to have some combinators there, just like with the features in Rust, like wait for both of them or wait for any of those two. And then once this stuff resolves, you want to maybe have some callback. Then unit test integration tests are tricky with smart contracts, because if your smart contract like a struct with the impl section and you just like call one smart contract from another, you have direct dependency, and it's really hard to mock. And then the blockchain also creates a hard dependency there. So what we can do to solve this is use dependency inversion and also dependency injection to break all these dependencies and make it unit testable. So the way you would write the smart contracts that call each other is by having traits that implement those smart contracts, and then you have dependency on the traits instead of the smart contracts themselves. And you can also have a trait for the blockchain. And so when, for instance, I want to test smart contract A, I inject with the mock the blockchain, smart contract B, and then I run them on my unit tests, and I can test them. Or if I want to integration test A and B, how they interact with each other, I can just inject mock the blockchain itself. And this is the code, the example of the code that would do such thing. You see it's basically the same struct incrementer. I also added another secondary smart contract called decrementer, and then incrementer calls decrementer for whatever reason, it doesn't matter. And the way we would declare this dependency is that we would have this blockchain and decrementer fields in the incrementer. And when you serialize them, they serialize into nothing. They basically behave like phantom data in Rust. They just like, they fake. And the way you would create a promise is like this. This is like an old style promise. And then you would use another macros to actually add the callback in there. And this is it. You can call decrementer from the incrementer here. And then you have a callback would be calling decrement result. So that's how we can have synchronous cross-contract calls in Rust. This is pretty much it from me. This is our team. We are 14 people, like a bunch of Googlers, Facebookers, and all kind of competition winners. If you're interested, you should contact us. And this is the link to our website. Thank you.
Question time.
So maybe that's a really stupid question because I don't know much about smart contracts, but I didn't really get the jump from the beginning of your presentation where you were talking about the Amazon Lambdas and stuff like that to your smart contract. So are you saying that instead of executing code on Amazon, I should run it on your blockchain, or what is the, maybe you can give some real world application for that technology?
I mean, that is always the question with the blockchain talks, is that like, what's the application, right? So that's how I try to call my presentation smart contracts and on blockchain. But, well, so what I was saying there is that if you care about decentralization, right, then you need to run smart contract and not AWS Lambda. Now the question is, why would you care about decentralization? Why people do care about centralization? One of the motivations I brought in is that even if you don't care about like trust and privacy related things, your codes are just more robust on the blockchain. Especially like if you have no engineer and overhead to maintain it, and if it goes down and there is no engineer around to fix it, then it's pretty bad. While with the blockchain, it's quite unlikely that the blockchain is going to go down because there are so many people backing it up. But there are also applications of the blockchain in general, which kind of also gives the motivation for the smart contracts. And like the classic one is so-called the self-sovereign data, which basically think of like, let's say you're a Lyft driver, right? Or Uber driver, and you have these ratings and reviews about you. And then one day you decide to switch. If you're Uber driver, you want to become Lyft driver. And you cannot do it these days because then you're gonna be driving for 2 weeks with low rating, and that's kind of demotivates you from switching. That creates a moat around the business where it should not be. If your profile was on decentralized system like blockchain without company owning it, then you can just jump between different companies like Lyft and Uber and whatever is there, and without sacrificing your profile, without losing your rating and reviews. So this is like one of the examples. The second one is the accountability is easy. So this is like semi-real example. So let's say you want to move goods in between like farmers, right? So what you do, you put trackers on them, on the bags, and then you record it on the blockchain. And farmers want to do this because this is like a rating system for them. Like they know, that's like a Yelp for farmers. You know whom to trust. They're like, oh, this farmer is responsible because I can see the history of their transactions. Now the cool thing is that the government is interested in doing that too because the taxation is so much easier. Because it's all there on the blockchain. You don't need to go through the paperwork. It's so easy to compute it. So there are like at least 2 use cases there. And the self-sovereign data is the big one because it's not just about like Lyft and Uber drivers. People who are writing games, they want your profile to be also like transferable and reusable everywhere. And stuff that you collect in one game, maybe you want to sell it somewhere else. Like there are so many secondary shady markets out there with those online games, with those more PG, like World of Warcraft, that people are just doing like black market selling of their goods. So why not make it legal? Why not allow people to just go through some decentralized structure?
Two questions. First one is, why Rust? So is it because of the language, or is it because of a certain investment in the ecosystem which has been made by a certain number of blockchains, which then made it relevant as a target language. The second one is you mentioned WASI module for blockchain. Is that going to be part of the overall standard, or is that something that just blockchains interested parties are kind of standardizing towards?
Okay, so I'm gonna start with the second one. So WASI is a big project going on its own.
Yes,
in
exactly.
the
That's why I'm
WebAssembly
asking.
world, right? And the vision of the WASI is that you're gonna have modules for all kind of stuff. Like
Okay.
you're gonna have a module. Where is it? You're gonna have a module called like 3D graphics. That's there in the initial announcement. There are sensors, crypto, and other kind of things. And then one of them is smart contracts. So it was envisioned from the beginning when they were creating, like initializing WASI project, which is still they're debating on the standards there, that smart contracts would be one of the modules in it.
Okay.
Because then, I mean, if I write a smart if I develop a blockchain that says if you only call functions from this module, then it's going to be compatible with other blockchains, and it's really great because
No, I mean, I see the value. I was just curious to understand if it was part of the larger effort.
yeah, I mean, people who are just invested in a blockchain, they're pushing, I mean, their own vision of what the smart contract module is going to be, just as much as people who are interested in 3D graphics are pushing, you know, their vision for the 3D graphics module. That's why it's modular. Why Rust? Well, right now there are pretty much two languages that are compiled into WebAssembly, and they have like wide support. It's TypeScript, but not exactly TypeScript, assembly script, but it looks almost like TypeScript, and Rust. And why is it so? Well, historical reasons, I guess. I hope there are going to be many more languages in the future that are compiled to WASM, and then because they are running on WASM anyway, and they support, and WASI is the part of, you know, of the WASM ecosystem, then it wouldn't matter whether you're writing your language on Rust, C, or like whatever compiles to WASM and follows the WASI standards.
So it's about the compilation target, mostly.
Yes.
Can you tell us a little bit about the size of the smart contracts in the bytes?
Yeah.
This is the first question, and the second question is, what are the advancements compared to like Solidity, where you had millions of lost money and that were logical errors, not memory safety stuff?
That's the second one. Question is really great. I wanted to talk about it, but I didn't add the slides. So Rust is very generic Turing complete language. It's really hard to do formal verification on it and prove that certain things are not going to happen, like in terms of the money. But some of the formal verification you can do on Rust, and we're already doing. Specifically for the cross-contract calls, which are kind of asynchronous, we can actually explore all possibilities, even like that have really small chance of happening, of how they can call each other. Because, you know, if you make asynchronous calls, like you don't know what is the order, how they're going to go through. So there's a tool in Rust called Loom that allows you to do the exploration of the space of possibilities for the concurrent code, and we already use it for like raw threads. It doesn't support Tokyo yet. It supports raw threads and like mutexes. We can emulate our cross-contract calls through that and just like use it straight away. And then if you don't have like unbounded, they call it unbounded space of possibilities of what can happen, then we can just iterate through them, and sometimes it actually works. Smart contracts are super small. They're like really good for the formal verification because it's scoped small. Regarding size, it's like 20 to 40 kilobytes if it's like a very primitive program. If you have more stuff in there, it goes up to 200 kilobytes. But it's fine because we are able to run. We actually, right now, we are running Ethereum virtual machine in WASM. Like we want to run Ethereum contracts in WASM. So the way we did it is we're running an Ethereum virtual machine that runs the Ethereum contracts, but it all runs in WASM. It's like a nested Russian doll there. And this stuff is like 200 megabytes or something. I don't remember. So, but the problem with that is we want to incentivize people from doing this kind of thing. So the larger your smart contract is, the more money you pay for it. But like for 20 kilobyte, 40 kilobyte contract, it should be like so negligible that you won't even notice it.
No, just I ask for the size because like the non-Turing complete Bitcoin smart contracts, although they are limited, there are some bytes.
Yeah.
So like that's I'm afraid that these kind of systems they are hiding some bugs that are very difficult to find out, and especially when you are deploying these smart contracts, it's very difficult, almost impossible to change afterwards. So
no, in our case, you just redeploy it.
You're supporting a like new
totally.
version. Okay.
I mean, we have like self-upgrade and all kind of upgrade mechanisms there. But like, we don't delusion ourselves thinking that whatever we write right now is like there to stay.
Yeah.
This thing is
this is a good thing. Yeah.
And but like blockchain, Bitcoin, they had a rudimentary scripting language in there, but then the whole reason Ethereum happened is that it was rudimentary. It wasn't enough, right? So the Ethereum happens with a more powerful scripting language, and suddenly people talk about, the second generation of the blockchains, just because they have a different scripting language in there. So the power of the scripting language matters. And regarding these hidden vulnerabilities, there are other projects invested into actually figuring out all the vulnerabilities issues in WASM, specifically browsers who use WASM. So they will figure it out. It's not just us trying to look into this. It's like there are many, many parties involved in figuring out security vulnerabilities in WASM. The whole WASI project, like half of it is figuring out, like having a better security access control system for whatever you can run in this code. So it's a very large community.
Any other question? Okay, thank you.
Thanks.